Hello, pre-calculus. In this video, I'm going to continue Chapter 8, Section 5, which I had started before. We did example 1 and 2. This is example 3. These are more difficult trig equations, solving more difficult trig equations. And this one is asking us to solve 3 cosine squared x plus 2 cosine x equals 1. Okay, so in this situation, unlike example 2, where in example 2, we had a sine and a sine, but we didn't have a constant that did not have a trig function in. In this case, we do. We have minus, we're going to subtract 1 from both sides, set it equal to 0. But as you can see, we have a cosine squared, a cosine, and a 1. Well, we're going to treat this like it's a quadratic. What would you do if you had 3x squared plus 2x minus 1? Well, we would do the box method to solve this quadratic, and it's already set equal to 0, which we did already. That's what you want to do first if you had a quadratic. And then we're going to use the box method to solve this, to factor this quadratic. So a is 3 because of this leading coefficient. Make sure you have the squared first, and then the regular x, and then the constant. A is 3, b is 2, and c will be negative 1. You take a times c and get negative 3 and b. You're looking for two things that multiply to negative 3 and add to 2. Those two things that multiply to negative 3 and add to 2 would be positive 3 and negative 1. They add to positive 2 and multiply to negative 3. Okay, so then we're going to do the box method, but instead of x's, we're going to use cosine x's. So this would be 3x squared in a normal quadratic, but in this case it would be 3 cosine squared. And then we're going to use, that's my a. The first part of the box is always ax squared. Then it's rx, sx. We're splitting the b up, and then c goes into the last box. If you're doing box method, now I know some people might not have done this method, and you could do any method you want to factor the quadratic. You don't need to do box method, but this is how I did it, and this is how I taught algebra 2, which I know I didn't have you guys in algebra 2. But so ax squared is 3 cosine squared. B cosine, not B, sorry, R cosine. So my first of the B that split up into those two parts, R cosine, S cosine. So 3 cosine, negative cosine, and then the negative 1C. And yes, you could, if you had the 3 down here and the negative 1 up here, it wouldn't matter. You can switch these two. But it's always A, the last one's always, the first one's always A, the last one's always C, and then the B gets split up between R and S. Then you're factoring anything in common out this way, and 3 cosine squared and 3 cosine both have a 3 cosine in common. So I'm pulling that out. I'm factoring anything in common this way. There's a negative in common. I'm pulling that out. Down, I'm looking at so I just factored the rows. The columns, 3 cosine squared and a negative cosine. I'm pulling a cosine out. There's nothing in common. When there's nothing in common, you pull 1 out. You can double check this by looking if this 1 here and this negative 1, these two multiply to get negative 1, 1 times negative 1. 1 times 3x squared multiply to get 1 times 3 cosine x multiplies together to get 3 cosine x. I'm going to go over here, cosine times negative 1 multiply together to get cosine, negative cosine, and cosine times 3 cosine multiply together to get 3 cosine squared. So my two factors are 3 cosine squared minus 1 and cosine plus 1. And if you would FOIL these, you would go back to this, and that's the idea, reverse foiling. So our two branches now are setting each of these equal to 0. 3 cosine x minus 1 is equal to 0. Cosine x plus 1 is equal to 0. All right, solving each of these for, first we're going to solve for cosine x. So we want to get cosine x by itself. That's pretty easy to do on the right side. On the left side, I take one more step to get there. Then once we have cosine x isolated for both of these, we do inverse to actually solve for x. So my two branches will be x equals cosine inverse of 1/3 on this side, and x equals cosine inverse of negative 1 on this side. Okay. Now again, remember, when we have cosine equal to, or sine, or cosine and sine, or cosecant and secant, those three, whenever they're equal to 1 and negative 1, you're going to be, and also 0, when you're equal to 0, you're going to be between quadrants. So since you're between quadrants, and I can jump back to this graph again. Sorry about that. There we go. So here's the graph, and we're looking at cosine now, not sine, I believe. Are we doing sine or cosine? Well, it doesn't matter. Let's look at both of these. So sine is 0, then it goes up to 1, and in the range between 0 and 2 pi, it will hit 1 one time at pi over 2. It'll go down to -1. It'll hit -1 one time at 3 pi over 2, and then it'll go back to 0. So when we have sine of x is equal to 1, there's only one value. 1 and -1 will be the only two values where you will only hit those numbers at one value, one angle measure. If you go a little bit below that, if you can think of a horizontal line here, you can see how it's hitting that two value. Sorry, I'm going to actually use a window here to as a horizontal thing. So if you look at the top of this window, you can see how I'm hitting this horizontal line at, let's say, 1/2 is hitting it twice. There's two values that the horizontal line's hitting the curve. But when you get all the way up to the top, it's only going to hit it at one point. There's only one point. There's only one x value that goes to 1, and there's only one that goes to -1. I don't know if that makes sense. Same with cosine, though. At the very top, you're going to hit 1. You're going to go down through all the values. You're going to hit -1 only at one point, and that's going to immediately turn. Okay, and it's going to go through all the values that it just went through again, giving each of these other angle measures, each of these other ratios, two angle measures that give you those values. Now, when it gets back up to 1, remember that's going to be 1 again at 2 pi, but we don't include 2 pi. Our range goes from 0 to 2 pi, strictly less than 2 pi. So we're going to include this one, but not this one. I hope that makes sense. Which one are we on? 3. So we are looking at cosine, and we're looking at -1. Cosine, and if you remember the graph I just had up, cosine will be -1 at pi. But before we get to that, I'm going to do the left branch first. Cosine inverse of 1/3. So this is a positive, and there's solutions for cosine solutions are in first and fourth quadrants for positives. We are doing the normal solve this equation, simple equation for this. You plug 1/3 into your calculator, cosine inverse of 1/3 in your calculator, you get 1.231. Since it's the first quadrant solution, that is also our reference angle. We're solving using the reference angle formula and solving for x to find what the fourth quadrant solution is. So plugging this in for alpha, and we add x to both sides, subtract this 1.231 from both sides, 2 pi minus 1.231, 5.6. So that's two of our solutions. This branch will only have one solution because of what I was just trying to explain in the other. So it's going to be 3 total solutions, 2 for this, 1 for this. And that will be pi, exactly pi. I rounded pi to 3.142, probably because I'm already rounding the other two solutions because there's no exact for that. So, also, if you put that in your calculator, my calculator shut down. Second here. Need to reload it. Must have accidentally shut it down. Nope, don't want to be covered by my little box with my head. If you put, okay, so I'm doing cosine inverse of -1. So cosine inverse of -1, you will get that, and that is actually pi. So if you realize that's pi, you can just put exactly equal to pi. I probably did the rounded because of the other two were rounded, so I was just being consistent with my values being 3 decimal places. So hopefully that makes sense. Example 4. So what we have here is a similar one to the previous, but there's a big issue with example 4, and that is that we have a cosine squared and a sine. We have 2 different trig functions. Well, we can't do what we just did in the last one if the trig functions are different. that box method that we used has to have all the same trig function in it. But fortunately, because we have the trig Pythagorean identities, we can actually take a sine squared and we can actually change that, or sorry, cosine squared, and we could change that to sine squared because cosine squared is equal to 1 minus sine squared. So I'm replacing the cosine squared with 1 minus sine squared, making sure there's parentheses around it because it's 2 times this, so it's 2 times all of this. Okay, and again, this is the trig identity that says sine squared plus cosine squared is equal to 1. And sine squared plus cosine squared is equal to 1. Then you can subtract sine squared from both sides, so cosine squared is equal to 1 minus sine squared. Okay, so, and just make sure there's parentheses. I distribute the 2 in. I have 2 minus 2 cosine squared. And then this minus sine squared minus 1 is just following along. Okay, well then I have a 2 here and a minus 1 here. They can combine to a plus 1. And then my leading coefficient is now negative 2 sine squared. Okay, then the minus sign just followed the whole way down, didn't change at all. This got changed because of the 2 that was out in front. It is easier to do these. This is equal to 0, so I can actually multiply both sides by anything I want, and it's easier if the leading coefficient isn't negative. So I'm just going to switch the sign of everything. I'm switching the sign of 2. I'm switching the sign of so it's negative 2 to 2. Switching the sign of negative sign to positive sign, and I'm switching the plus 1 to negative 1. And then I'm switching 0 to 0, because 0 stays 0 when you're switching it. This right here, 2 sine x squared plus sine x minus 1, will factor to 2 sine x minus 1, sine x plus 1. So that is the box method that is outlined over here. If you need to do the box method to factor, A would be 2, B would be 1, C would be negative 1. Multiply those together, get negative 2. Two things that multiply to negative 2 add to 1. They are 2 and negative 1. You put them in, you pull, and then that's how you get those two factors. Okay, I'm not going to go through all that again in detail. So my two branches are 2 sine x minus 1 equals 0, and sine x plus 1 equals 0. Okay, so solving both of these for the trig function first, add 1 to both sides, divide both sides by 2, and you get sine x equal to 1/2. Over here, you just have to subtract 1 from both sides, and you get sine inverse, or sine x is equal to negative 1. I'm just going to go down a little bit here, and then you take the sine inverses of both sides, and x will be equal to sine inverse of 1/2. This is a normal trig function that we're going to do with the two quadrants and the reference angles. This here, though, again, equal to negative 1, 1, or 0 is different between quadrants. Sine inverse of negative 1 will be a specific answer that we will look up in a minute. But first, let's do the left branch, which is sine inverse of 1/2. Solutions for sine positive are in quadrants 1 and 2. I'm actually going to do this with exact numbers because 1/2 shows up on the chart that you should have memorized a while ago. Let's see if I can find it here. This chart here, remember this chart? Okay, sine 1/2 is pi over 6. Okay, that's where I'm getting the pi over 6, and I'm getting it exactly because I want to be a pro here. Now, in the actual problem, I mean, it would be okay in a problem if you did the approximately. So, like, if you didn't notice that, I'm not going to take points off if you did approximately, as long as you do approximately equal to and you use the values that are approximate, like the correct decimal values, is what I'm trying to say. But, man, if you see that this is an exact pi over 6, man, that's some top-notch stuff then. So I'm going to go through this entire thing as pi over 6. So as my alpha as pi over 6. So first of all, my first quadrant x angle measure is pi over 6. Because it's first quadrant, alpha is equal to theta, so my reference angle is pi over 6. Okay. Quadrant 2 reference angle formula is alpha equals pi minus x. I'm plugging in pi over 6. And for alpha, I'm solving this. So add x to both sides, subtract 6 pi from both sides. So we have 1. Essentially, we have 1 minus 1/6, which is 5/6. So it's 5 pi over 6. Okay, so then we're going to look at sine inverse of negative 1. So this is a between the quadrant solutions, and if you remember the graph, let me jump back to the graph. For sine, we're looking at -1. It's going to be 3 pi over 2. 3 pi over 2 is the answer for that. Because I had exacts up here, I want to do the exact here. If you didn't realize the exact for that, because you did it on your calculator, it's a decimal value. Oh, actually, it's going to give you the negative. So I have to add 2 pi to that to find the coterminal. Get that, and that is 3 pi divided by 2. Okay. So your three answers are pi over 6, 5 pi over 6, and 3 pi over 2. Okay, so that is example, 4? I think there's one more example in this section. Let's see here. And sure enough, there is. Let's do this, and then this will be it for this section. So we're solving tangent squared minus 5 tangent plus 6 equals 0, and we're in degrees. And so this is factoring just like we've been doing in the last two, except this one you don't really need to do box method for, because when there's not a leading coefficient, you can just do two things that multiply to this and add to this. So it's two things that multiply to C and add to negative, or add to B. -2 and -3 are the two things that multiply to 6 and add to -5. So this factors tangent -2, tangent -3. Again, you can double check that by foiling. So setting each of these equal to 0, if tangent is equal to -2, tangent of theta -2 is equal to 0, add 2 to both sides, and then we're going to take the tangent inverse of both sides. Over here we have tangent of theta -3 equals 0. So tangent is different. Unlike sine and cosine, that's restrained between -1 and 1, tangent doesn't get restrained between 1 and -1. So that means the rules that I was saying about sine and cosine, if it's -1, if it's 1, there's only one solution. Those go out the window for tangent. So tangent will always have two solutions, even when they're between quadrant solutions. Let me just double check that before So if we want to look at a graph, I'm going to do this on the graphing calculator of tangent. I'm going to do tangent of x. My mode is radian. Maybe I'll change that to degree. Let's see how this works. And then I want to do zoom trig 7. Okay, so this is the graph of tangent. So really, in this graph, it's going from -360 to 360, or just shy of 360. I'll just change it to 360. I'm not sure why. It's not quite that. So now let's just look at 0 to 360. So you'll see, because sine over cosine is, the definition of tangent is sine over cosine. When cosine is 0, you're going to have division by 0, which would be undefined. And that's what's happening when you have, or at here, which would be pi over 2, and here, which would be 3 pi over 2. You're having division by 0, because, right, cosine is 0 at these two values. And when sine is 0, you have 0 over a number. That happens at 0 and pi. So you see how it doesn't matter what it doesn't matter what cosine is when sine is 0, although it's 1, but it's 0 over 1 is 0. Okay, so that's what's causing these zeros here, and that's what's causing the undefines. But what's important to note is that this, like if I change the window to negative, let's say 10, just make the window bigger. And I'm only changing the vertical, not the horizontal. Still 0 to 360. You can see this graph just goes up. This is an asymptote. That's what I'm trying to say. Okay, it'll go up forever. But the important thing to note about this is, unlike the graph of sine and cosine, if you have tangent equal to an integer, that still is going to end up being two solutions, because any horizontal if I do this whole thing with this window like I was doing before, any horizontal value as you go down through here will always have two solutions. Okay, do you see that? It's always having two solutions, even at 0. At 0, the solution would be over here and here. Still has two solutions. So that rule where if it's equal to 1 or -1, that's only for sine, cosine, and their reciprocals, and not for tangent or cotangent. That's my point. And so this is the graph of tangent. So whenever you have tangent, you always have two solutions. So tangent positive will have solutions in first and third quadrants. So I'm going to look at the left branch here first. And so I do tan inverse of 2, and I need to make sure I'm in degrees because I changed it for that. So tan inverse of the number 2, I get 63.4, and if it's degrees, you only have to do 1 decimal point. Radian, you should do 3. 63.4 degrees. That is also the reference angle. The third quadrant, tangent's positive in the third. The third quadrant reference angle formula is alpha equals theta minus 180. So I'm plugging in for alpha, and I'm adding 180 to both sides, and I get 243.4. Okay, then I'm going to do the same thing with the second branch here, the right side. I'm going to solve for tan inverse of 3. Well, this is also positive, so you have another set of solutions in the first and third quadrant for this. So I just go back to my calculator. I do tan inverse of 3 now. It's going to be a different measurement, 71.6. That's my reference angle because it's first quadrant, and I do the whole quadrant 3 thing again. So I'm actually going to end up with 4 solutions for this, 2 solutions in the first and 2 solutions in the third quadrant. Okay, and I just put them in, I don't know if you noticed this, but I've been putting them in numerical order when I summarize at the end. So hopefully I didn't go through that too quickly. The one thing I didn't do in this video is double check my answers. And there is some bookwork that I will assign. I'll have that posted. But if I wanted to double check one of these solutions, so I'm looking at tan squared minus 5 tan plus 6, and I'm going to see if that equals 0. We'll see if I can remember that. Let me pick just one of these. So remember tan, it'd probably be better to do tan inverse, no, sorry, tan, just do tan of an angle measure first. Get the value. That's pretty close to 3, right? But I'm going to just take answer. I'm going to do second answer squared, and then let me screw up here and do minus 5 second answer plus 6. Now this should be equal to 0. It's probably going to be a little off, but it should be pretty close to 0. Yeah, it's a little off. Probably it's because we rounded, right? This is a rounded answer. I'm wondering if this shouldn't be 3, and if I had 3 squared minus 5 times 3 plus 6. Yeah, see? So the actual value when you plug this in would be, when you plug this rounded degree in, should be 3, which actually makes sense because that's what it was here, right? And that causes this to go 0, so that's what makes it one of the solutions. Okay, so, well, hopefully this makes sense. Again, more difficult trig equations. They're a lot of work. So in a work packet, this would definitely be 1 problem per page situation going on here. But anyway, thank you and good day.